In this video, the entire video, the directions are evaluate each integral. So we will have to pay special attention to whether or not there are limits on the integral, making it a definite integral, or if there are no limits, then it is an indefinite integral, and we will need to remember to add that plus c at the very end. All right, let's start. So for this particular integral, I see no limits, so I know that right off the bat, I'm going to say don't forget plus c. We will need that as part of our answer. So how do we find the antiderivative of this thing, or how do we integrate this thing? Well, first I see a problem here with this cube root, and I want to rewrite that. So this would be 5t cubed minus t to the 1/3 power dt. Now that this has been rewritten as an exponent, we can use the power rule to find the antiderivative, which will be 5 times the antiderivative of t cubed is t to the 4th divided by the new exponent, minus, that's this minus here. The constant multiplier here is 1. I don't need to write anything for that, but I will have t to the 4/3 when I add 1 to that exponent. And instead of dividing by this new exponent, since I have a rational exponent, I'm going to multiply by the reciprocal plus c. And so I can just clean this up a little bit. I'm going to write 5/4 t to the 4th power minus 3/4 t to the 4/3 power plus c, just to make it look a little nicer. This notation here is a little clunky, so just to make it look a little nicer, I just rewrote it. And that's the antiderivative for this. For this example, this looks pretty ominous, and if you know anything about integration by substitution, you may want to try that here, but I'm going to urge you to not. What you want to notice, first of all, this square root, that is bothersome. So I want to rewrite that. I want to rewrite that as x cubed minus x plus 2 all over x to the 1/2 power dx. That makes me feel a lot better. Anytime I see a root, I feel like instantly rewriting it, because this does not help for integration, whereas having a power does. All right, next I will notice that there's only one term in the denominator. And what that allows us to do then is split up this integral into 3 terms. So I'm going to have x cubed over x to the 1/2 minus x over x to the 1/2 plus 2 over x to the 1/2 dx. Now, why would you ever want to do this? Well, we can simplify this fraction and this fraction, and since this has no x's in the numerator, we can bump this x to the 1/2 up to the numerator. And we can get x to the 5/2. That's what happens. 3 minus 1/2 is 5/2. Minus x to the 1/2. Again, 1 is the exponent here. 1 minus 1/2 is 1/2. Plus 2x to the negative 1/2 dx. And now that everything is in the numerator and we have an exponent for everything, we can now run through and find the integral of this expression. So this becomes, let's see here, add 1 to the exponent is 7/2. And I want to multiply by the reciprocal of this exponent because I see it is a fraction. So I will say 2/7 x to the 7/2 power. This next one will be minus let's see, so minus, I'm going to add 1 to this exponent here, that would be x to the 3/2, and I want to multiply by the reciprocal out front again, instead of dividing by a fraction. I don't ever want to divide by a fraction. Multiply by the reciprocal makes it simpler to understand. And lastly, I have plus 2 times the antiderivative of this variable, which is x to the 1/2. And again, I have a fraction for the exponent, so I'm going to multiply by the reciprocal. Plus c. No limits of integration here, no numbers here on the integral sign, plus c. So this simplifies. The only thing we have to simplify here is this 2 times 2. So this simplifies to the following. And that's it. We just had to multiply this 2 times 2 to get 4, but everything else is the same. And that's it. Here's our integral of this. For this example, we are looking for the indefinite integral, or otherwise we're looking for an antiderivative of this nonsense, dx. And so we don't have a very good way to do this. Well, what can we do here? We can try looking at this as secant and tangent both being squared. So we could try to do something like this: secant x over 3, tangent x over 3, the entire thing squared, because we would just distribute this square here and here, but that's going to make real big troubles when we try to set our u equal to secant x over 3, tangent x over 3, and now we have a product rule, and that's too much. So we can't think of it like this. So there's got to be an easier way. If we let u be equal to just x over 3, that's not going to work either here, because the derivative du would be 1/3 dx. And if we let that happen, then we would just end up with a secant squared u times tangent squared u. In this case, it would be times 3 du if we multiply both sides by 3. And that's not going to work either. So we've got to think of the relationship between secant and tangent. Let's see here. If we let u equal secant, that's it, just secant x over 3, the derivative of that would be secant tangent, and that's not going to help either. My goodness. So we probably should try u equal tangent x over 3. du in this case would be secant squared x over 3 times 1/3, because of the chain rule, dx. And I think this will work out really well, because when I rewrite this indefinite integral as, let's say it's going to be u squared, because the tangent here is being squared. What we have left over will be, what do we have? Secant squared x over 3 dx. So all of this, all of this got replaced with u, and it's being squared. And so here left in our integral, we have secant squared x over 3 dx. Now it's really close over here. We just need the secant squared x over 3 dx, but we have this extra 1/3 being multiplied in here. So if we just multiply both sides by 3, we will have exactly what we need to make the secant squared x dx substitutable for 3 du. So all of this is going to turn into 3 du. We still have this integral u squared 3 du. And just like I do with any constant when I'm using substitution, I'm going to pull or factor the 3 to the front of this integral, u squared du, and that just makes it easier, like focus on the u squared here. So now I can actually find the antiderivative of that, 3 u cubed over 3 plus c. And these 3's very nicely cancel out, leaving us with just u cubed plus c. And finally, since we started with x's, we have to end with x's. Right now we're still in u. So u is tangent of x over 3. So we finish our answer with tangent of x over 3, the entire thing being cubed plus c. So you can either write your answer this way, or you could, if you wanted to, write your answer this way. Either answer is fine. This answer down here, this second one, lets us know exactly the same thing. It's the tangent that's being cubed, not the x over 3 that's being cubed. But this top answer gets a little clunky with the extra set of parentheses that you'll need. So either one is fine. I'm going to go out on a limb, say most teachers / professors would prefer this bottom example, or this bottom answer. But make sure you check with that person to see what they like. All right, now we're getting into some fun stuff here. We have the definite integral of some absolute value function. And this is one that we are not going to directly integrate. We're not going to find an antiderivative of this. We're going to look at a graph of what this function looks like. So this graph is an absolute value function that was shifted right 1 unit. So here we go. So it's doing something like this. And let's see, it goes from -2, so like right there, to +3, something like right there. And so we're looking for this area here. So we know this is 1. We know the base of each of these triangles. The base of this triangle is 3. The base of this triangle is 2. As long as we can find the heights, we are good to go. And luckily, this absolute value function is uses a slope of 1. It's hiding right in there. So that means the height of this triangle is also 3. And the height of this triangle is 2. So all we have to do now is find the area of this entire triangle, or this entire space here. So we can go through and find this one first. We can go through and find this one second, and just add our 2 areas together. So the area of the first triangle is 1/2 base times height, which is 4.5. The area of the second triangle is 1/2 base times height, which is 2. If you add these 2 things together, you get a total area of 6.5. Next example, more integration. So we are asked to find or evaluate this integral, and this one's going to be a little bit different. We still need to use substitution, and again, we're looking for some inside function. I see it here. It is 4 minus x. So I want my u to be equal to 4 minus x. That's fine, and then we have a du equaling negative dx. So when we make these substitutions, we get that the next integral will be x over u cubed, right? 4 minus x cubed, we substitute u in for 4 minus x to get u cubed in the denominator here, dx. And then we need x dx left over. So we come up here and we look at this particular equation. We've already used this one, so we just need to use the second one. And you say to yourself, hey, yeah, here I have a du equaling negative dx. Well, I need an x dx. And you out there watching this video, you're no dummy. You say, hey, I want to multiply both sides of this equation by x and get x du equals negative x dx. And then we divide by -1 to make this happen. You say, hey, I get this. This is going to be u something over u cubed, and the x dx turns into x du, and this is still a problem. Here we have u's, fine, but this x, that can't be there. We can't have an x when we're trying to find the indefinite integral with respect to u. So this is a huge problem. We cannot do this. So what are we supposed to do? Well, we have to go back and manipulate this top equation again to be, let's see, we have to solve it for x, which ends up making it x equals 4 minus u. Now what does that accomplish? So we can't do this here, but what that allows us to do then is to rewrite this particular integral as 4 minus u over u cubed, because 4 minus x is equal to u. That's fine, so we replace that with u. But if we solve for x, now x is equal to 4 minus u, which allows us to replace this x in terms of u. Now for the dx, right, I have not done anything with that yet. We can change it to du by using this equation here, and just multiplying by -1 to get a negative du. So we're not using any of this here either. So this turns into negative du. So we have an integral of 4 minus u over u cubed times a negative du. And again, with that any constant that I have here like this, a constant multiplier, -1, I like to pull it out to the front. So this would be negative integral 4 minus u over u cubed du. All right, so we have all of our constant multipliers in front. We have this new function, and apparently this is supposed to be easier to integrate or more manageable than what we started with. And you might be wondering, well, how? How is this any better? Well, like we had a few slides ago, if you notice that there is only one term in the denominator, that this can be broken up into multiple terms. So I'm going to do that, and we'll say this is equal to negative integral of 4 over u cubed minus 1 over u squared. Now mind you, there's been some simplification there. 4 over u cubed is 4 over u cubed, but the second term is u over u cubed. You can cancel the u in each one and get 1 over u squared. So now we will rewrite. This will be negative integral 4u to the negative third power minus u to the negative second power du. And now we can find the antiderivative of both of these. So we have a negative, how does this work? 4u to the negative 2 power, because we're going to add 1 to the exponent and divide by the new exponent, minus u add 1 to the exponent, divide by the new exponent, plus c. And again, we have this plus c here because there are no limits of integration anywhere in any of these, so we have that plus c. Now for some simplification, I will have a negative, let's see, the 4 over negative 2 becomes a negative 2 u to the negative 2. And again, here we have a negative 1 divided by a negative 1, which makes it plus u to the negative 1 power plus c. And then I get to distribute this negative here and here. So I end up with 2, let's see, 2 over u squared, because we also bump this to the bottom, minus, because of the distribution of this negative here, 1 over u to the first plus c. Now, final step, we started with x's, we need to end with x's, and this is still in u. So we just remember way back over here that u is equal to 4 minus x, and we get to substitute that 4 minus x in for both of these to get a final answer of 2 over 4 minus x squared minus 1 over 4 minus x plus c. On this slide, we will have the final example for this already too long video. So I will try to get through this as quickly as possible. In this particular instance, we want u to be the square root of x plus 3, which more appropriately ends up being the x to the 1/2 power plus 3. And if we find du, you'll notice that if we use the power rule here, bring the 1/2 to the front, and subtract 1 from the exponent, that makes it x to the negative 1/2, which I'm going to immediately bump down to the bottom, dx. If you can remember that 1/2 is the same thing as a square root, you can see we have a 1 over square root of x here, dx. We also have that here as well. We have the over square root of x, dx. So let's get to substituting here first. Let's do this. We have sine of u all over x to the 1/2 dx. So I need this 1x to the 1/2 dx, but this x to the 1/2 in the bottom, kind of like we have going on right here. But I need to get rid of this 2 somehow. If I multiply both sides by 2, I get rid of it there. And so I can say that this entire piece here gets replaced with 2 du. So this would be sine of u times 2 du. And again, I want to bring this to the front of the integral. And so that leaves me with integral 2 integral sine of u du. And now we can just go ahead and find our antiderivative of the sine of u, which will be negative cosine of u plus c. So multiply a negative 1 times a negative 2 to get a negative 2 cosine. And then we replace u back with what we started with x's here. And you can use either one of these, either the square root of x plus 3 or x to the 1/2 plus 3. Either one works. I like exponents, so I will use x to the 1/2 plus 3. And we've arrived at our final answer here.